Good morning, everyone. Today we will look at the proof of, of a very important theorem in elementary number theory. It's Euler's theorem, and this theorem is a generalization of Fermat's last theorem. Uh, you probably know who Fermat is. Fermat's last theorem, everybody knows about that. So he also gave another theorem in number theory, Fermat's little theorem, and it states that if a is any integer and p is a prime number, then a raised to the power p congruent a mod p. And this Euler's theorem is the generalization of this theorem. So if you are wondering where did Fermat's little theorem came from, it came from Euler's theorem, which we will be proving today. Now, the rest of the video is based on the assumption that you already know about the torsion function, Euler's torsion function, which states that all the positive numbers, torsion of m is all the positive numbers less than or equal to m, such that m and ai equals to 1, gcd of m and ai equals to 1. Now, for the proof, we need two more things, and that's complete residue system, a definition of solids, and reduced residue system. Now, for the complete residue system, it's if x congruent y mod m, then set of all xi such that it or we can say xj uniquely corresponds to some y, xj congruent y mod n. Well, this is very theoretical, so let's just take a simple example. Suppose we are considering 4, so possible remainders of 4 will be this is not an official notation, we are using it for convenience: 0, 1, 2 and 3. So if we consider a set such that all the numbers in the set is uniquely correspondent to each of these numbers, then we call it a complete residue system, modulo 4. So if I were to think of it, then I can write it as 4, 5, 6 and 7. So this corresponds to 0, this to 1, this 2 and this 3. So this set is a complete residue system modulo 4, and a reduced residue system is a bit different. It states that all Ri, where R1, R2, so on and so forth to Rn, is co-prime to M. So Ri modulo 1 mod. So all possible Ri's. If we look at an official definition for it, so it also states that all numbers co-prime to M are congruent to some unique Ri. Okay, pretty understandable from the definition itself. Now we will look at another definition. This will be the final one. This will be the final definition, I promise you. The final definition is that if GCD of AM is 1 and we have a reduced residue set, we call reduced residue set, this is an unofficial notation, mark my words, of R1, R2, so on and so forth to Rn, then reduced residue set or complete residue set, doesn't really matter, then A R1, A R2, so on and so forth to A Rn is also a reduced residue or complete residue set mod M. Okay, so this is the final definition, and now let's look at our theorem. So the theorem states that if GCD of A and M is 1, then this condition is satisfied: A tangent of M congruent 1 mod M. Now, how do we prove it? So the first idea that should come to one's mind will be use of something like this, use of this particular definition, a particular theorem. So we can consider a reduced residue set, which is of the form, let's call it S, R1, R2, R3, so on and so forth to Rn, R tangent M, tangent of M. Okay, now why is this R tangent of M? It is for a special reason. We'll discuss it as we move forward in the proof. So we have got this, and now using this theorem, we can say that AR1, AR2, so on and so forth to AR tangent M is also a reduced residue set. So product of this can be written in the form of A raised to the power tangent of M, and this is Ri from 1 tangent of M is congruent to tangent of M, product of this mod M. Now I know that all of our i's are congruent 1 modulo M, so product of all of our i's will also be congruent 1 modulo M. So it's so by this we can say that A raised to the power tangent of M minus 1 multiplied by Ri tangent of M I equals to 1 is divisible by M, where M divides this number. Now I know that M is co-prime to this, so I know that M, sorry for the mistake, M is co-prime to this. So that must mean that M divides A raised to the tangent of M minus 1, and this can be written in modular arithmetic form as A tangent M congruent 1 mod M. And that's our proof. Thanks for watching.